Welcome students to the lecture series on Rolle's theorem and mean value theorem. So before going to the main Rolle's theorem and mean value theorem, we will need to know what is continuity of a function and differentiability of a function. So suppose we have a function a which is defined on a subset D of the set of real numbers to the set of real numbers, and let C be a point from D intersection the derived set of D. Then we say that f is continuous. We say that the function f is continuous if and only if limit x tends to c, fx, which is equals to the functional value at the point c, that is fc. If this condition holds, then we say that the function f is continuous at the point c, and if f is continuous at all the points of D, then we say that the function f is continuous on D. Now differentiability. Suppose we have a function f which is defined on the closed interval ab to the set of all real numbers, and consider C be an interior point, that is C from the open set A to B, then we say that the function f is differentiable at the point C if the limit at as x tends to c, fx minus fc by x minus c, this limit exists. And if this limit exists, then we say that f is differentiable, and we will denote it by f dash c. Next, if we say that the function f is differentiable at the point A, which is the left hand point, if as x tends to a plus limit this limit exists, and we say that the function f is differentiable at D if x limit as x tends to b minus fx minus fp by x minus b, this exists. Also, if C be an interior point, then the right hand derivative at the point C, we will denote it by limit when x tends to c plus fx minus fc by x minus c, provided the limit exists and the left hand limit is given by this limit x tends to c minus fx minus fc by x minus c, provided the limit exists. And we say that the derivative at the point C of the function f exists provided these two right hand limit and left hand limit are same. Now consider a function fx is given by mod x. Then we will check the differentiability of the function fx at the point x equals to 0, and for that we will first find the right hand limit at 0, which is equals to limit x tends to 0 positive fx minus f0 by x minus 0, which is nothing but limit. Now when x is positive, then mod x is we know mod x is just x, and at 0 mod x is 0, so x minus 0 by x, so this is nothing but 1. And if we calculate the left hand limit at the point 0, then this limit gives limit x tends to 0 minus. Now in this case fx is minus x and f0 is 0 by x, which is minus 1. So clearly you see that the left hand limit and right hand limit for this function mod x is not equal. So therefore fx function is not differentiable at 0. Now we will see the Rolle's theorem. What are the statements of Rolle's theorem? The statements say that if we have a function f from the closed interval ab to the set of all real numbers, we such that the function f is continuous function on the closed interval ab, and f is differentiable at every point of the open interval ab, and fa equals to fb, then this theorem tells that there exists at least one point c which lies between a and b such that f plus c becomes 0. Now it should be noted that the set of conditions in the Rolle's theorem is a set of sufficient conditions in the sense that f dash x may be 0 at some point between the open interval a and b, even if the conditions of the theorem do not hold together. For example, we consider this function fx given by mod x plus mod of x minus 1 when x lies between minus 1 to 2. Now clearly from the definition of modulus, we can see that the function fx is 2x minus 1 when x lies between 1 to less equals to 2, and which is equals to 1 when x is from 0 to 1, and 1 minus 2x when x lies between minus 1 to 0. So clearly f is a continuous function in the closed interval minus 1 to 2, and but f is not differentiable at the point 0 and 1. Also f of minus 1 and f of 2, which is equals to 3. So therefore f does not satisfy the second condition of the Rolle's theorem, which states that fx must be differentiable at every point between the open interval minus 1 to 2. We see here that f is not differentiable at the point 0 and 1, which is lies between minus 1 to 2. That means the function fx does not satisfy the second condition of the Rolle's theorem. But you see that here fx is just 1 when x lies between 0 to 1. What does it mean? That means f dash x equals to 0 when x lies between 0 to 1. So although f does not satisfy all the conditions of the Rolle's theorem together on the interval minus 1 to 2, but f dash x becomes 0 at some points in the open interval minus 1 to 2. Now what is the geometrical interpretation of the Rolle's theorem? If a function f has a graph which is a continuous curve on the interval closed interval a to b, and the curve has a tangent at every point on it with abscissa between the point a to the point b, and the ordinates, that is the height here fa and fb, they are equal, then there exists at least one point c which is lies between a to b such that at the point c comma fc on the curve we have a tangent which is parallel to x-axis. Now see some examples. The first problem is verify Rolle's theorem for the function fx equal to cos x in minus pi by 2 to pi by 2. Now we know that the trigonometric function sin x and cos x, the function sin x and cos x. So here we have the function cos x. So fx equals to cos x. We know that this is continuous and differentiable for all real values. So therefore, clearly cos x is continuous on the closed interval minus pi by 2 to pi by 2 and differentiable, cos x is differentiable on every point between minus pi by 2 to pi by 2. Also, f of minus pi by 2, that is cos of minus pi by 2, which is 0, and f of pi by 2 equals to cos pi by 2, which is again 0. So therefore, the function fx equal to cos x satisfies all the three conditions of the Rolle's theorem. Therefore, by Rolle's theorem, we should have a point C such that f dash C becomes 0, where this C lies between minus pi by 2 to pi by 2. Now the function fx is just cos x, so therefore f dash x is minus sin x. So from here it is clear that minus sin c equals to 0, which implies sin c equals to 0, whose one solution is just 0, and clearly this 0 lies between pi by 2 to minus pi by 2. Hence, we have a point 0 lies between minus pi by 2 to pi by 2 such that f dash c becomes 0, or f dash 0 becomes 0. So therefore, Rolle's theorem is verified. Okay. Now the second problem, verify the Rolle's theorem for the function fx equal to mod x in the closed interval minus 1 to 1. Now here the function fx is given by fx equals to mod x when in the interval minus 1 to 1. We know that the function fx is continuous on the closed interval minus 1 to 1. But previously we have proved that the function fx is not differentiable. Fx is not differentiable at x equals to 0. That means this function fx equal to mod x does not satisfy the second condition of the Rolle's theorem. Therefore, Rolle's theorem cannot be applied for this function. Okay, and the next theorem is mean value theorem, and it is also known as Lagrange mean value theorem. If we have a function f from the closed interval ab to the set of all real numbers be such that f is continuous function on the closed interval ab, and f is differentiable at every point of the open interval AB, then there exists at least one point C from the open interval AB such that f dash C equals to Fp minus Fa by B minus A. Now see the another form of mean value theorem. Here we consider just B equals to A plus H. We replace B by A plus H in the above theorem. Then this theorem tells that if f is a function from a comma a plus h to the set of all real numbers such that f is continuous on the closed interval a comma a plus h and f is differentiable at every point of open interval a comma a plus h, then there exists a real number theta which says theta lies between 0 to 1 such that f dash a plus h equals to f a plus h f dash a plus theta h. Now see the geometrical interpretation of the Lagrange mean value theorem. If the function f has a graph which is continuous curve on the interval closed interval AB and the curve has tangent at every point on it with abscissa between a comma b, then there exists a point C between a to b such that at the point C comma fc on the curve the tangent is parallel to the line segment joining the point a comma fa and b comma fb. Also it should be noted that the Rolle's theorem is the particular case of Lagrange mean value theorem. Why? Because from this theorem, if we take another thing, that is the last condition of the Rolle's theorem which states that Fa equals to Fb, and if we put here, then we see that f dash c becomes 0 when Fa equals to Fb. Okay, now see this problem. Verify the Lagrange mean value theorem for the function fx equals to x into x minus 1 into x minus 2 when x lies between the closed interval 0 to half. Now here the function fx is x into x minus 1 into x minus 2, which is equals to x into x square minus 3x plus 2 or x is cube minus 3x square plus 2x. Now this is a polynomial. Now clearly a polynomial function is always continuous and differentiable for all values of all real values or all values of r. Then f is obviously continuous on the closed interval 0 comma half and differentiable. So clearly, since f is a polynomial function, then clearly fx is continuous on the closed interval 0 comma half and it is differentiable at every point of the open interval 0 comma half. So that means the function fx satisfies the two conditions of Lagrange mean value theorem. So fx satisfies all the conditions of Lagrange mean value theorem. Now here f dash x is 3x square minus 6x plus 2. Okay. Therefore, since it satisfies all the conditions of Lagrange mean value theorem, so therefore we should have a point C such that f dash c equals to f of half minus f of 0 by half minus 0, where this c must lie between 0 comma half. Now this is 3c square minus 6c plus 2 equals equals to, now fx is x cube minus 3x square plus 2x. So x cube minus 3x square plus 2x. This gives 3c square minus 6c plus 2, which is equals to 2 into 1 by 8 minus 3 by 4 plus 1, which is equals to 1 minus 6 plus 8 by 8, which is equals to 9 minus 3 by 8, so into 2, so 3 by 4. That is 12c square minus 24c plus 8 minus 3 plus 5 equals to 0. So now if we solve this one, then we can see that c equals to 1 plus minus root over 21 by 6. Clearly, the value 1 minus root over 21 by 6, this is lies between half and 0. Thus, for the function in here fx, the Lagrange mean value theorem is verified. Now see the next problem. Prove this inequality where the function, where the variable x is strictly greater than 0. For this one, if we consider the function fx equals to log of 1 plus x, then this function is continuous for x strictly greater than 0 and differentiable also. So now we can apply the Lagrange mean value theorem for the function fx equal to log of x plus 1 plus x on the interval 0 comma x. Then by using Lagrange mean value theorem, is fx is theta x, where this theta is lies between 0 comma 1. Now fx is just log of 1 plus x and f of 0 is log of 1, which is 0 plus x and f dash theta h. Now fx is log of 1 plus x, so f dash x is 1 by 1 plus x. That is 1 by 1 plus theta x. It is equals to log of 1 plus x equals to x by 1 plus theta x. Now since theta lies between 0 to 1 and we know that x is positive, so if we multiply by x, then we will see here this becomes 0 theta x less than x. Then this is 1 plus theta x less than 1 plus x, which implies that this is greater than 1 by 1 plus theta x is strictly greater than 1 by 1 plus x. Now see here, 1 by 1 plus theta x is just 1 by x log of 1 plus x. So multiply again by x, then x by 1 plus theta x x by 1 plus x, which is x greater than log of 1 plus x, which is strictly greater than x by 1 plus x. So log of 1 plus x is strictly less than x and strictly greater than x by 1 plus x. So hence the problem is good. Also, students, you can practice at home these problems. Thank you.